Okay, everybody, welcome back. We are beginning to take a look at functions, and I am going to tell you a little bit of the story. All right, anytime you have an equation of any kind, both of these are a relation. There is a relationship going on between x and y. Don't you see they're both in the same equation? So they're going to interact. They have some kind of relationship. Now, you can see a relation. It's really another place to see it is ordered pairs. All of the numbers in here are x's and y's, and they have a relation. The x's and y's are all connected. Now, somebody was looking at all of these relations, and as mathematicians are prone to do, they began to see a pattern, and so they took something that they saw and they gave it a name. And so a relation is any time two variables have this relationship. But what they did was they went ahead and they solved them for y. And so what they did was they set this up as if it was a machine. Now notice here that when I had to take the square root to get y by itself, I got a plus or minus. Okay, now here's what I mean by the machine. I want to put something in for x. The machine is going to crunch on it. It's going to multiply by -3 and add 5, and then y is going to come out the other side of the machine, right? Now here I put something in for x, it crunches on it, etc. So the input, or the independent value, is that x, because we've set it up like a machine. And the output, or the dependent variable, the output here is the y. It's dependent because it depends on what you put in for x. Okay, now I'm actually going to skip a lot of what they say up there and just tell you my story. So imagine that you had a machine and you're putting x's into the machine and y's are coming out of the machine. Now when they were looking at these equations like this, mathematicians began to notice that there were some special kinds of machines. And what would happen is you would put a number in the machine, and out the other side you would get a single number. I have a, well, that's not it. So like I have this picture of the elves. This is supposed to be a present. Oh man, I'm not an artist. Okay, so a toy goes in. Little car goes in, and it comes out the other side and it's wrapped. That is supposed to be a bow on top. It is not very good. Now, a functional machine is one in which you put something into the machine and out the other side you get a single gift, one gift. It would not be a very functional machine if you put something into the machine and suddenly two things came out the other side. That would be very odd, very unusual. So mathematicians saw this. If you have the relationship, you got it set up like the machine where y equals something. And if you put something in for x and you get out only one number for y, then you have a functional machine. And it gets the name a function. If you put something in for x and two things come out the other side, that's very strange. That is not functional. It is not a function. Okay, so let's look here and see why they've got a lot of squiggly things up here. Okay, these are my x's and my outputs are my y's. I have this one going to over here. He makes one thing. If I put q into my machine, he makes one thing. If I make r in the machine, he makes one thing. Now look at this. It doesn't matter that there's two ways to make the letter n. It doesn't matter. The only thing that makes a function is if you put one thing in, you put something in, and you only get one thing out. So that's a function. That's good. Now look here. This one does too. Every letter that you put in, you get one thing out. But this one's not. Notice that if I put the letter P in, that one works. But if I put in Q, out the other side of the machine, somehow miraculously, I get both Y and Z. This is not a function. All right, now we have a whole nother lesson on the domain and the range. That's our next lesson. But the domain are the things that you put into the machine, and the range are the things that you get out of the machine. Okay, so in our case, all of my illustrations, the domain is our x values, the ranges are y values. All right, now when it gets that notation, I think there's something I want to add here. So when it gets this special notation, we just call it f of x. And how we say it is that y is a function of x. It means if you put x's into the machine, you get one y out. Okay? And it gets this special notation. But this is still y. It is exactly the same thing. It's a fancy notation, but it is still y. It just lets you write something like this. This means if you put 1 into the machine, you'd solve it, you get 3, 4, you get 5 out. This is still the point 1, 5. Just like it always was. This will really confuse people, but that's just a notation to say this is that special machine. Now, you can do this in any kind of application you want. We want to see if price is a function of the item. Okay, that means the item is going in the machine. So if I put a plain donut in, I get $1.49 out the other side. That's fine. Jelly donut in, I get $1.99. Chocolate donut, $1.99. Now that's okay. There were two of the same things that came out the other side, but one donut did not have two different prices. That would not be functional. Now let's try the other way around. Is the item a function of the price? Okay, so price is going in the machine. Do you see what will happen when I put $1.99 in the machine? Out the other side will come jelly donuts and chocolate donuts. That one's not a function. Okay, some of these illustrations they have I don't think are all that important. I would certainly not test you, but here's the deal. If you were to put in, I don't know which way they're trying to say, but let's say is grade point average, no, I should say is percent grade a function of your grade point average? Percent GPA. That would mean that if you put one of these numbers in the machine, you should only get one number out. Okay, well, is that true? Well, we put in this one, we get a whole range of numbers. Now, none of them repeat, so that's actually okay. Let's try the other way around. How about GPA and percent? So is GPA a function of percent? Well, if you put in any of these numbers here, you get the different, you get 0.0, you get 1.1, you get 1.5. Okay, I actually paused it because I got confused by my own story here. So we were saying, yeah, I find this chart very confusing. To make sure I was right. Okay, so is GPA a function of percent? Okay, well when we put in percent into the machine, I'm putting in 0, I get 0.1. I put these, so that works, but the other way around, if I put 0.0 in, I get multiple outputs. Multiple numbers come, all the numbers between 0 and 56 come out of there. That's too many numbers. This one is not a function. All right, I'm not going to have you pause it on this, so let me just talk you through here. So is rank a function of the player name? So here's what we're saying, rank name. So if I put a player's name into the machine, I get out one rank on the other side. That's okay. Now how about the other way around? Okay, if I put the rank in the machine, do I get one name out the other side? Yeah, I do. So this works either way. One name goes in, you get only one thing out. Same for rank. Okay, I showed you this already. This is just a confusing description of what I said. So this notation means it can be anything. So let me say it like this again. If this is that special machine, it gets this notation. It's still y, but it just gets that fancy notation to tell all mathematicians that that's that special function. And you'd say y is a function of x. Okay, sorry, I'm flying through these, but it's all the same things I just said. Okay, there's some of these here in the middle I skip in a college class because I don't think it's very important. But all right, so we have a function where what they're saying is if you put in the month, you get out the number of days in the month. Well, this is going to work because every month only has one number of total days, so this is a function. Now they're asking us to interpret one here. So there's a lot about the notation. I wouldn't spend this much time on it, but in the year 2005, you put it into the machine, you get 300 police officers out. That's what it says. So, okay, the weight of a pig as a function of its age in days. Okay, weight in days. So if I put in the number of days old a pig is, I'm going to get out his weight. Is that a function? Yeah, it is. A pig can only weigh one thing at a time. When he's 3 weeks old, he's 21 days old, he's got one weight. So this is a function. So days goes in, his weight comes out, and it's not two things at the same time. Now you will see something like this. You'll see tables. Sorry, I'm taking a drink there. I spilled water all over my keyboard. Okay. Now, these are my x's and my y's. So what's going in are my x's here. So let's look at table 6 here. I'm putting 2 in, I get 1 out. All of these are fine. So this is a function. In here, I'm putting different numbers in. I get the same number twice, but I never have one number make two things. So that's a function. Now, this one does not work. Do you see? Because when I put in 5 into the machine, I get 2 numbers out. Not a function. Okay, let me just talk you through it, or pause it if you want to try, I guess. But we are putting in these numbers, and every x only creates one output, so we're okay. That's a function. All right, now we're going to talk about evaluating functions. All this means is that you are going to put in the number. What do they got here? Yeah, they did a good job with this. So I am putting 2 into the machine. The special notation lets me know that I put 2 into the machine, but all I'm doing is replacing the 2's, or the x's with 2's. Now just be careful of the order of operations. 2 squared is 4. So we work this through. And this is an ordered pair. It's 2, 6. It's still an ordered pair. I put 2 in, I got 6 out. Now let's look at some of the weird ones that can happen. If I put in A, there's nothing else I can do. But as we start to move towards calculus, this is a really important idea. We can put in anything into this function. And this is a clever way to get an idea of, well, we're heading towards something called a secant line and eventually derivatives. So what I'm going to do is I'm going to put A into this function, and that's it. There's nothing that can reduce or combine. I guess you could try to factor this, maybe, if it works. I don't think it does. It might. But there's nothing else to do. The best you can do is put in an A. Now, watch what happens, though, if I put in A plus H. I've just replaced all the x's with A plus H. Now, when I'll have a student try to work this in class, they'll think, oh, well, this part here, you got to reduce this. They're going to say, well, this makes A squared plus H squared. No, it doesn't. Because when you multiply a binomial, you got to FOIL it out. Now notice here, when I go here to here, I'll get AH. And when I go here to here, I get HA. But these are being multiplied, and so 2 times 3 or 3 times 2 are the same thing, so it doesn't matter. These are the same thing. So what you get is A squared plus 2 of those AH terms in the middle plus H squared. Now they distributed the 3, and they had the minus 4. Now if you could go farther, you would, but nothing here combines, and you would be finished. Again, now we're really hitting the calculus idea because this is what they're doing here. The next one they wanted us to do was this, where we are going to try to find this function. It's a trick. It has to do with slope. And so let's do it. So we have a plus h going into the function, which we already did. We already did f of a. We'd have this. So now look what they want us to do. I'm going to take that first answer minus the second one, and we're putting it all over h. Now this minus sign is going to change the signs of everyone who follows. Let's see how they did. Well, they skipped over a bunch. But when he becomes negative a squared, he'll cancel. When he becomes negative 3a, he's going to cancel. He becomes positive 4, they're going to cancel. So a ton of stuff cancels out, and you'll only have this left right here. Now, you pull out a GCF out of there. You got an h on the top and the bottom, and you can cancel those h's. Now we'll talk more about that later, but if it's a factor on the top and a factor on the bottom, it can cancel out, and there you go. All right, now we're going to evaluate some functions. This is really quite simple. All I'm doing is putting 5 in place of m, and I've got equals 1. Now, I don't know if, I'm sure there'd be a better place to talk about this, but square root isn't normally a function in and of itself, because if you square root 9, you're going to get plus or minus 3. So if you put one thing into a square root, you would get two things out. Like if I put 9 in, do you see what I mean? So this would not make a function. But the way they fix this is they work with something called the principal root, which is just the positive value. So if you see here, I put 5 in, but they've said this has to be a function. So normally when I would square root, it'd be plus or minus 1, but that would not be a function. So I'm just going to take the positive. Okay, here's another one. We're dropping 4 in for our p. Just be careful of the order of operations. That's all there is to it. All right, now this one is going the other way around. What they're doing here is they're telling us what comes out of the machine. So I know that p squared plus 2p equals 3. And hopefully you remember your factoring skills. To solve something like this, we need to get 0 on the right side. Now let's factor. So I factor that, I get p plus 3, p minus 1. And we have something called the zero product property. Lets us set either one of those equal to 0. There's a lot going on the screen, but we just set them both equal to 0. And so there are my answers. Okay, let's do another one. Pause it if you want to try it on your own. They're telling me m minus 4 equals 2. Now do you remember how to solve something like this? I want to get rid of the square root, so I will square that side. But if you do it to one, you got to do it to the other. And m is 8. All right, now what I really want you to see here on this slide, I'll tell you what's going on, but what I want you to see is if you ever start an equation with a y squared or a y to the 4th or whatever, this is not going to be a function because it's going to require you to square root it. And so that is going to involve a plus or minus. So this is the equation for a circle. A circle, as we'll talk about more in our next video, is not a function. So, because at one particular x, you get two y's up and down. Now, there's a way you could fix it. So here's what happens if you naturally do it. Now, what I was telling you about earlier is that they fix this problem by choosing what's called the principal root. They choose just the positive, or else you wouldn't be able to get a function. So you could work the circle as two different functions is the only way you could fix this. The positive side and the negative. Okay, this is not something I'm all that interested in either, but what we're seeing here is so I want to cube root this. Yeah, I could just go ahead and do this here. So I want to cube root this so I can set this up as a function machine, which remember it means y is by himself. So I'm going to have the cube root of x over here, because if I do it to one side, I got to do it to the other. Now cube roots don't have this issue because I can take the cube root of both of these sides. I can take the cube root of everything on the right. That gets me -2, because -2 times -2 times -2, that's fine. So the problem is only with y squareds. Okay, even numbered roots. Okay, so I'm almost done. I'm just going to divide both sides by -2. I'm going to flip this around so it looks like this. And now I have this set up as a function machine. And there's nothing wrong with cube roots. That's a function. All right, now that's an introduction to just this special notation that is called a function because someone noticed this pattern that if you put something into the machine, you're not supposed to get two things out the other side. We'll continue that in our next video.